Information on the periodic table. The number and type of valence electrons primarily determine the chemistry of an atom. Electron configurations can be determined from the organization of the periodic table. Certain groups in the periodic table have special names. Elements in the periodic table are basically divided into metals and nonmetals. Elements that exhibit both metallic and nonmetallic properties are termed metalloids or semimetals. So here are the names of some of the special groups in the periodic table. Column number 1 is called, or group 1A, are called the alkali metals. And this is because when you take a metal like lithium and you put it in water, it's going to produce hydroxide, and that hydroxide makes something basic, and the term alkali describes something that is basic. Alkali earth metals are metals that are often found compounded with something else. Right? So they're found in rocks, and that's why they're called alkali earth metals. But they're going to do the same thing. So if I take magnesium and I burn it, it's going to turn basic. Okay? Working the other way, we've got our noble gases. They're so called because they do not interact with anything else. Next up is our halogens in 7A. So fluorine, chlorine, bromine. Next are the chalcogens, so oxygen and sulfur. This comes from chalk forming elements. 5A are called the pnictogens. So that's nitrogen, the column headed up by nitrogen, and that means the choking elements because you cannot breathe pure nitrogen. Right? This D block is often called the transition elements, and then we have the lanthanides and actinides. Those are our F block elements. If we categorize it in terms of metals and nonmetals, our nonmetals are all over here in the upper right-hand corner. Most of the elements on the periodic table, including the lanthanides and actinides, are primarily going to be metals. And kind of along a diagonal here, there's a transition where we got the metalloids or semi-metals. Right? So our metals are going to occupy most of the left-hand side of the periodic table. Things like magnesium, copper, and gold. If you look at copper, silver, and gold, they actually fall in this little column here. These are called the coinage or noble metals. That's because they're resistant to oxidation. So something like a ferrous metal like iron will rust. Gold will not rust. Copper is hard to tarnish in pre-industrial society, and the same thing with silver. Over on the right-hand side, we've got our nonmetals. So our metals, they're shiny, they're lustrous, malleable, ductile. Over on the right, we've got our nonmetals, so something like iodine, sulfur, phosphorus, oxygen. A lot of these guys are gases. So our metals, shiny, lustrous, malleable, they're good conductors. They've got low ionization energy. They tend to form cations. They form ionic compounds with chlorine and form basic ionic compounds with oxygen. Our metals are refer to the properties of metals such as shiny, lustrous, malleable. Metallic character increases down a group. Metallic character decreases across a period. Metals have low ionization energies, and most neutral metals are oxidized rather than reduced. When metals are oxidized, they tend to form characteristic cations. Group 1A metals form M plus cations, and Group 2A metals form M2 plus cations. Most transition metals have variable charges. So when you get into the D block in the middle, that's where things get a little complicated. Nonmetals vary in color. They tend not to be shiny. They tend to be brittle, poor conductors. They're going to form acidic molecular compounds with oxygen. They're going to have a high electron affinity, so they're going to form anions. Metallic character increases from top to bottom in a group and decreases left to right across a period. So our metalloids, for example, silicon, which is shown here, has a metallic luster, but it's brittle. So it's kind of got characteristics of both. Metalloids have found fame in the semiconductor industry. So we really rely on some of these metalloids to do everyday things like silicon, germanium. These guys are important to us. Our semimetals, they are going to include about 7 elements, so boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Astatine is not very common. It's radioactive. It doesn't stick around very long. Properties intermediate between metals and nonmetals. They tend to be silvery in appearance and solids at room temperature like metals, but they're brittle and poor conductors of heat and electricity, like nonmetals are. Our alkaline metals, lithium, potassium, sodium, rubidium, cesium, francium, calcium are the most chemically reactive of the metals. They're never going to be found in nature in a pure elemental state. You actually have to do quite a lot of work and put in some energy to go from a sodium-containing compound to reduce it to sodium metal. Hydrogen exhibits a non-metallic character due to its small size. So hydrogen acts like a gas just because it's so tiny, although people have theorized that you could find metallic hydrogen, say, in the core of gas supergiant planets, and they are trying to actively look for evidence of that. Going down a group, ionization energy decreases, atomic radius increases, density increases, melting and boiling points kind of decrease smoothly. The alkali metals are soft silvery metals. They react with water to form alkaline products. They're never found in nature in their pure state. Their chemistry is dominated by the loss of their single s electron, so an M. So our metal is going to form M plus and an electron. And they react with water to form a metal hydroxide and hydrogen gas. So like M could be lithium or something, right? So 2M plus H2O is going to give us the corresponding metal oxide and hydrogen gas. Group 2A, alkaline earth metals, are lustrous silvery metals. They're less reactive than their Group 1A counterparts, but they're still never found in nature in a pure state. Some will react with water to form H2 gas, and some will react with acid to form H2 gas. The Group 2A alkaline earth metals are harder and more dense than the alkaline metals, but their chemistry is dominated by the loss of two s electrons. So our metal is going to form a +2 cation and 2 electrons. So magnesium will react with chlorine to form magnesium chloride, or two magnesiums will react with oxygen to form magnesium oxide. Beryllium does not react with water. Magnesium will only react with steam. From calcium onwards, we have a reaction where the calcium is going to react with water to form calcium hydroxide and H2 gases. This is pretty much the same reaction that we saw with the alkali metals. Group 3A, so our NS2NP1, are going to be metalloids or metals. So beryllium is a metalloid. Aluminum is going to form Al2O3, aluminum oxide with oxygen. Aluminum forms a +3 ions in acid, and others are going to form either a +1 or a +3. Our group 4As are going to be our NS2NP2, so our nonmetals like carbon, our metalloids like silicon and germanium, and other metals form 2+ and 4+ oxidation states. Tin and lead react with acid to produce H2. Group 5A, NS2NP3, 2 plus 3 is 5. Nonmetals, these are nitrogens, nitrogen, phosphorus, metalloids, arsenic, strontium, and metal, bismuth. Nitrogen forms a variety of oxides, phosphorus, P4, arsenic, bismuth, those are all going to be crystalline. Nitric acid and phosphoric acid are important industrial. There's a big stick of phosphorus there under oil, and that's some liquid nitrogen. Group 6A, the chalcogens, are going to form they're nonmetals, going to include sulfur and oxygen and selenium, and the metalloids tellurium and polonium. So we're going to form SO2, SO3, H2S, H2SO4. Oxygen, silicon, tellurium, and polonium are electronegative elements strongly associated with metal-bearing minerals, where they have formed water-insoluble compounds of metals in the ores. They're called chalcogens, both because most ores are copper, or chalcos, or oxides or sulfides, and such ores contain traces of selenium and tellurium. The halogens are group 7A, colorful, corrosive nonmetals. They're very reactive, and they're almost always going to be found combined with other elements. The chemistry of the halogens is dominated by gaining an electron to form an anion. So do X2 plus an electron gives you 2X minus. Fluorine is one of the most reactive substances known. So there's a cool video, and I should post it, where basically it will burn through anything. Fluorine is on the list of chemicals I refuse to work with because it's dangerous. So 2 fluorine gas plus 2 water is going to give you HF. and O2, and it's going to be exothermic. It's going to generate a lot of heat. So if you have a fluorine fire, right, the advice is forget about it. It's gone, because what do you think your ordinary rules are for putting out a fire, right? You throw water on it. All that's going to do is rip that oxygen apart. It's going to form hydrofluoric acid and oxygen gas and a bunch of heat and make your fire worse, right? Your backup standby, throw some sand on it. It's going to do the same thing. It's going to rip the oxygen out of the SiO2, and it's still going to catch on fire. So if you got a fluorine fire, it's just like you just wait for it to be done burning, and then you carry on. So all the halogens are going to consist of diatomic molecules X2. Chlorine is the most industrially useful halogen. It is produced by the electrolysis of brine, sodium chloride solution. You take sodium chloride and water, and then you can put in some energy in the form of electricity, and you can form sodium hydroxide, hydrogen gas, and chlorine gas. The reaction between chlorine and water produces hypochlorous acid, which is what disinfects the water. So when they say you're adding chlorine to the pool, you're actually making hypochlorous acid. So the chlorine gas is going to react with H2O to form HCl and perchloric acid. Hydrogen compounds of the halogens are all strong acids with the exception of HF. Group 8A, or 18, are the noble gases. So it's the NS2, NP6 configuration, 2 and 6 is 8. They're all monatomic. They're completely filled shells. They were considered inert until 1963. And then they were able to form some xenon and krypton compounds. They really don't have a major commercial use other than in things like neon signs. You will sometimes see them in other bulb applications, but there's not a lot of use for the noble gas. Helium is important for filling balloons, and it's important scientifically, but not on an industrial scale. So to summarize, we got groups 1A to 8A, those are our main groups, and then we've got 1B to 8B, those are transition metals, and then we've got the lanthanides and actinides, which are often placed below the periodic table.